Hello, this will be a demonstration of proposition 13 from book 2 of Euclid's Elements, which states that in acute angled triangles, the square on the side opposite the acute angle is less than the sum of the squares on the sides about the acute angle by twice the rectangle contained by one of the sides about the acute angle, namely that on which the perpendicular falls, and the straight line cut off within by the perpendicular towards the acute angle. Let's draw all that out. So we're given an acute angled triangle, ABC, such that the angle ABC is an acute angle. Furthermore, from point A, we have the straight line AD perpendicular to BC, like so. And what we have set out to prove is that the square on AC is less than the square on CB plus the square on BA by twice the rectangle contained by CB and BD. Let's begin. First, we know that because BC has been cut at random at point D, we can leverage Prop 2.7 and say that the square on CB plus the square on BD is equal to twice the rectangle contained by CB and BD plus the square on DC. This is because proposition 2.7 tells us that if a straight line be cut at random, the square on the whole plus the square on one of the segments equals twice the rectangle contained by the segments plus the square on the remaining segments. In this case, we have the whole BC split up into segments BD and DC, and we can say that CB squared plus BD squared, this being the whole, the square on the whole plus the square on one of the segments equals twice the rectangle contained by the segments plus the square on the remaining segment. The first segment we use was BD, so that makes the DC the remaining segment. And by common notion 2, we can add the square on DA to both sides so that we can say that CB squared plus BD squared plus DA squared equals twice the rectangle contained by CB and BD plus DC squared plus CA squared. Again, that's just common notion 2, adding the square on DA to both sides. Next, by proposition 147, we can say that because we're dealing with the right-angled triangle BAD, we can say that the square on AB, which is on the side subtending the right angle, is equal to the square on BD plus the square on DA, BD and DA containing the right angle at D. Similarly, by proposition 147, when we look at the right-angled triangle ACD, we can say that AC squared equals AD squared plus DC squared. And so figuring out where we can find these identities in the original quality, we find that we can combine BD squared and AD squared into simply BA squared, so that we can say that the square on CB plus the square on BA equals twice the rectangle contained by CB and BD, plus combining DC squared and DA squared plus AC squared. And moving things about in the equation, or in the equality, we can say that AC squared is less than CB squared plus AB squared by twice the rectangle CB by twice the rectangle contained by CB and BD. And this being what we have set out to prove, we are done with the proposition, therefore, etc. QED. Now, like the previous proposition 2.12, which was a case of the law of cosines with an obtuse angled triangle, this is also a case of the law of cosines, but with an acute angled triangle. So, again, let us write out the equality by saying that AC squared equals CB squared plus BA squared, subtracting twice the rectangle CB times BD on both sides. We can say that AC squared equals CB squared plus BA squared minus twice the rectangle contained by CB and BD. And again, like the last time, the relationship between this proposition and the law of cosines all hinges around what BD is in relation to the other sides and angles. So let's look at this right angle triangle right here, BAD. simply, using cosines, we can say that the cosine of the angle ABC, which is the same as the angle ABD, equals the adjacent over the hypotenuse. The adjacent is BD, and the hypotenuse is AB. Excuse me. So that we can say that BD multiplying AB on both sides equals AB times the cosine of the angle ABC. Now, replacing this segment of our equality with that, we can say that AC squared equals CB squared plus BA squared minus, it's right there, okay, I see, minus 2BC times AB times the cosine of the angle ABC. Now, like last time, putting this in strict algebraic notation, calling this side A, calling this side B, and calling this side C. Again, naming sides after the lowercase of the angles which they subtend. We can say that B squared equals A squared plus C squared minus 2AC times the cosine of B. And this is a common form of the law of cosines. This is another form of the law of cosines. And so, having arrived at how proposition 2.13 relates to the law of cosines, I'm done speaking about this proposition, and I shall end the video here and move on to proposition 2.14.